In this video lecture I will discuss the so-called covariance test. The methods we discussed before, in particular post-double selection and disparsified lasso, rely on a particular value of lambda. So they don't take into account that you also need to estimate this value of lambda. Now, it seems that this does not seem too much of a problem if we look at how well the methods do in practice. But still, it would also be nice to have an alternative way of looking at the whole coefficient path and doing inference on that. And this is covered by the covariance test proposed by Lockhart et al. And essentially it's going to take the least angle regression algorithm, which gives us a solution for the lasso with the modification over the whole path of lambdas. And at every point we can do where we have a knot, where a new variable is coming into play, we can do a test, see whether this actually provides significant improvement. And this therefore gives us a very different perspective on the lasso and also on doing inference. So let's first briefly recap least angle regression. Now suppose we've done k-1 steps already. At that point, what do we have? Well, we have a value of lambda indicated by subscript k-1 after k steps. We have an active set of variables that are included in our model, put in the set A, k-1. So there are of course k-1 of them. And we have the coefficient vector at that point in time. Now how do we then proceed with least angle regression? Well, first we determine in which direction we should move. So we look at the least squares direction. We're going to move towards the least squares solution. So that direction is denoted by delta hat A. And then we're going to move all our variables towards their least squares value. So we're going to add that direction, and how much we're going to do that? Well, we're going to decrease lambda from this value on, and so this is the amount we're going to move towards the new coefficient vector, which of course is a function of lambda. So the smaller you take lambda, the more you move towards the least squares solution. And you're going to keep track of the residuals while you do so. So you subtract every time x times beta hat for a particular value of lambda from y, and those are our residuals. And then what the least angle regression says is, well, keep on moving until you reach a point where there's another variable which we have not considered yet. A variable, say xl, where L is not in the active set, which now has the same correlation with the residual as the variables that we already did consider. So all of the variables that we did consider have the same correlation with the residual by the fact that we used the same argument in the previous steps. Well, as long as the correlation with these variables with the residual is more than any other, we keep on moving towards the least squares solution, but we stop the moment we find another variable which has the same correlation with these residuals. Well, at that point we stop by defining what we call a new knot, so we sort of fix the next step for lambda k, to that particular value, and we add this variable L to our active set. So we create a new active set as the union of the previous one and this new variable. And we update, of course, also our beta hat to that particular point. Well, then we go back. Well, now, of course, we've step 0, we actually end up with a new set consisting of a k previous steps, and we go back to step 1 and do the whole thing over and over again. Now, if you want to actually get the lasso modification, we need to do a slight change in the least angle regression algorithm, and that is we need to drop variables if they change sign between knots. So if this beta hat for any particular variable moves from positive to negative or vice versa, so it crosses 0, then we also stop and we take it out of the active set. And now what we want to do is, whenever we reach this knot, whenever we include a new variable L, we want to test if that actually leads to a statistical improvement in fit. So basically what we're going to need to do is compare the beta hat values. Compare beta hat value without that variable, so active set ak minus 1, with a beta hat variable with that variable included. But of course, we need to be careful because the lambda should be the same. Because obviously, if you change lambdas, you also induce shrinkage. If you make lambda larger, you get more shrinkage, so it's not a fair comparison. So how do we then choose an appropriate lambda for which we do that? Well, you might say, well, why don't we take the lambda when we just add it? Because, well, at that point, we really switch from ak minus 1 to ak. But of course, at that point, we just add it, and it means there is no effect yet of the variable. We have not moved its coefficients yet towards the least squares solution. So what we do is actually go one step further, so we fully go through this step until we actually end up with the point where we add the next variable, which we then actually don't do. But at that point, we fully used up lambda to give the new variable its full effect before we actually move on to the next one. So at that point, lambda k plus 1, this is the best choice to actually perform this analysis. So what we then do is, well, what we get directly out of the algorithm is this beta hat lambda k plus 1, where we've added the variable L before and we've completely used up its effect. Then we need, of course, to have the comparison, because that one we don't have. So what we also do is we take the same lambda, the lambda k plus 1, but then again delete that variable L and run the lasso on that. So we do the lasso on this active set ak minus 1, but with that particular lambda. And then what we do is simply measure how much does the fit improve. Well, there are of course numerous ways in which you could measure that. What they propose in the paper is to measure that by the improvement in covariance between the data and the fitted value. Of course, the higher the covariance, the better you fit your y. So we want to see how much did things improve by adding the variable compared to not having added the variable. And that will then be our test statistic. Now the reason to choose this test statistic is that if we assume that actually variable L does not have a coefficient different from 0, so this variable is actually not important, then our test statistic converges to an exponential distribution. Whereas if indeed variable L does bring you important gains, so its beta is different from 0, you get a large test statistic, so you can reject the null hypothesis. Now, as you can imagine, in order for this test to work, it means that the beta j of the variable that you add should be large enough to detect. So you get a sort of beta min condition on that variable. So that you might think, well, okay, this is of course going to be a problem, but in this case, I would argue it's actually not so much of a problem because we take a very different perspective here. And it's the same for any hypothesis test. If the thing you test for is too close to the null hypothesis, you don't have power against. You will not be able to reject that. So in fact, if we have a small beta j, you will get insignificant outcomes of your test. But I would say in this case, this is not necessarily bad because probably indeed adding that variable does not improve the fit so much. It could have consequences if you want to do inference on a particular variable, but if you would want to do inference on a particular variable, you would not use this covariance test. It really has a different goal in doing inference.